Okay, so good afternoon, and sorry for this bit of a delay, but I think it is better to have a break in between. It is so that way it is good. So I'm Karthik Senapati from Physics Department, Niger, Bhubaneswar. So I came to know that this is I'm the only person representing Niger apparently, which is a bit strange, but anyway, there is some representation, so I am here. So my prime interest is actually we have a modest lab in Niger, which is focused on superconductivity and mostly on superconducting devices. Mostly, we also do a little bit of materials, refined materials. I'll tell about mention a little bit about those also. But my prime interest is superconducting devices, which are basically junctions and Josephson junctions and squids. Okay, and today, of course, I will tell a little bit about one experiment that we are doing. Uh, it, there is a bit of a problem, I think, but okay. So today I'm going to talk about this Josephson diodes, which are creating a lot of, a lot of ripples in this community. But before going there, I will, of course, take this opportunity to showcase some of the work that we have been doing in the past few years. By my old PhD students who have moved out to different places now. Okay, the first one is about spin triplet squid, which is unusual using. We made a device. These are just advertisements, so don't take it. Just take the references and all. So we managed to make spin triplet squid devices, which using ferromagnetic barriers between superconductors. And actually, squeezed using we squeezed the magnetic layer in the barrier to the level of so that we can trap one single magnetic domain, which can convert singlet to triplet. Okay, that way we managed to make a spin triplet squid, and also we managed to make um, recently I published something on Raspa-Edelstein effect, which we detected through a Josephson junction, planar Josephson junction. Of course, this is a buried. This was important because this Raspa-Edelstein effect happens at the interface of metal and a heavy metal interface, but that is buried inside. So, but we are able to detect it, detect the phase that it creates in a junction on the top. And we also do, as I was saying, we are also doing a little bit of material work, which one particular metal I'm involved in is this nickel bismuth, NiBi3. And one of the students actually managed to grow single crystal nickel bismuth nanorods, which are superconducting. Okay, very long, like tens of microns, so 10 of the order of 10 to 20 microns. Okay, so this is also very important because single crystal superconducting nanowires growing directly during the film growth of a thin film. It's pretty it's unusual, and there are not many ways, not many ways to grow single crystal superconducting nanowire. They're rare. So this is a very simple way. By depositing a film itself, we got a nanowire. So these reference one can see to get an idea of the details. And we also did using the techniques that we use nano squids. We managed to make a very tiny squid of the order of like 50 nanometer or so, which with which we studied a single molecule magnetic material. We managed to see some signature of magnetization tunneling in the molecule itself through the squid. Okay, so these are some of the work that we have been doing, just to give you a flavor. So coming back to today's presentation, I will be talking about Josephson diodes. Of course, this is a plan. Okay, so let me start quickly. So diodes, we of course know. We have been, it's very familiar device, PN junction diode. Basic feature is that you are able to more current in one direction and less current in the other direction, forward bias and reverse bias. That is a basic feature that is on which everything else is, all this thing is working actually. All the electronics are working. It has been a dream to realize this in the supercurrent version of this diode. Okay, whether it is in a simple superconducting track or in a Josephson junction. Okay, it has been a dream for some time. And what I mean, if I want to give a current voltage curve equivalent to this, then what I would expect is that uh, my current would be more in one direction, less in other direction, or ideally zero. Okay, here I am talking about supercurrent. Okay, that's the only difference. Okay. So this has been a dream, and people have been, and this is not a new field. I mean, it's as early as 2005, 6. You can see there are people have been trying to get this kind of asymmetric current voltage curve in superconducting tracks, for example. Okay, this Moschel group also using various extrinsic techniques. Okay, here, for example, they on a superconducting track they put a magnetic strip and generated a critical current difference, asymmetry, not difference, asymmetry between plus side and minus side in this way. And Mostelker group, they tried to compensate for the stray field on one side of the of a superconducting track by sending another current here, okay, generating a field through this current, so that you get an asymmetry. So there are like many different attempts have happened to get a non-reciprocal, so-called non-reciprocal behavior. And I also tried during my postdoc time, I also tried by putting a magnetic layer on an IBM track. I also managed to get quite a significant sort of asymmetry between the plus critical current and minus critical current. And more recent, you can see Jagdish Mudira's group also. So they have published like 2023 using a similar thing, but they use different material, urochrome sulfide and other things on an IBM track. Okay, but these are this has been happening. But what really kicked the kicked this field a little bit, kicked a bit of life into this field very recently is this Japanese paper. This is by Teoro Ono's group. What they did is that they made a multi-layer. Okay, so very very thin layers of each of them. And niobium is superconducting, and there is vanadium, tantalum, and ultra thin layers of these. Okay, so they made basically one single layer and made a track, and they saw that the uh, critical current is actually more in one direction compared to the other direction. So this is why this is important compared to earlier studies, is that now this is an intrinsic effect. In this one material you have you don't have an external effect, okay, field compensation, extra layer of magnetic material and so on outside, that is not there. So it is like a uniform single material. The entire thing is superconducting. That is the point. Okay, so that so they managed to get plus current less, or like different than the minus current, minus supercurrent. Okay, so the basic idea was that for this, behind this structure, you need to break in order to get a non-reciprocal response. You need to break inversion symmetry as well as time reversal symmetry. So in this case, inversion symmetry was broken by the structure, and time reversal symmetry was broken by the magnetic field which is applied. Okay, so both conditions are satisfied. So if you think in terms of, in terms of a simple band picture, what it does is that if you have an inversion symmetry broken, so then you have a K shift in the band. So it's a spin up and spin down. You can have a K shift, and if you have a time reversal symmetry broken on top of that, so then you can have an energy shift between up and down. This is by an external magnetic field, for example, or having a magnetic layer in between something. Okay, so then you can break time reversal symmetry, and you can have a Y shift between up and down speed. So then at the Fermi level, because you will be, for superconductor you need up and down pairing, right? So at the Fermi level you will generate some sort of asymmetry. Okay, that is what sort of triggers all these interesting effects. And it people describe it in different ways: magnetochiral effect, finite momentum pair, and so on. But ultimately it is all linked to this kind of asymmetry at the Fermi level, okay, in some way. And this group also later on, so this was in presence of an external field, and they replace the external magnetic field, replace the requirement of an external magnetic field using a cobalt layer on the top, which is ready-made magnetic moment. So that is breaking that is again satisfy the condition without requiring the magnetic field. So this is all good. Like this is what in the track, in a superconducting track. Okay. Now, so the bottom line is that we must inversion symmetry must be broken. Time reversal symmetry also must be broken. This is of course essential condition. This is not a sufficient condition. It's like if you have this, you will have diode effect. It is not true. Okay. Now coming to, so those are all in the superconducting track. Okay. Now coming to a superconducting junction like Josephson junction. What is the junction? Very briefly, you take two superconductors and put something in between which is non-superconducting. So then, if the wave functions, superconducting wave functions can overlap, if the boundary is thin enough, then you will have without any sort of voltage, you have a current which is Josephson current. And the important thing is that it is controlled by this relation, which is the very familiar Josephson relation, that the current is actually controlled by the phase difference across this barrier. Okay, so but then if you look at the junction, it is perfectly symmetric. So there is on the first look, you would not expect, I mean, why it would be different from this side to this side and this side to the current. Okay, so this has to be, so it's fundamentally symmetric. The current will also be symmetric. Okay, in a normal junction. But what important point is that what drives is the current is driven by this phase difference between the electrodes. Okay, now and these are basic like characteristic features of a junction you should look for when you make a device or study this. So this is like usual. If you apply magnetic field, the flux is quantized. So that this is essentially that flux quantization signature. You see critical current Fraunhofer patterns, very similar to optical Fraunhofer patterns. Okay, so using that idea, so one of the first papers was actually this by Christopher Strunk in 2022, where they used aluminum based. So this aluminum, and then there is 2D gas here. Okay, so the superconductor, the coupling, Josephson coupling happened through this aluminum, this thing, the 2D gas system. So there, they essentially use this RASPA, so interface RASPA. So this has a very strong inversion symmetry breaking field here, and then you have this, you can have this magnetic field and so on to break the other one. So ultimately, because they tapped into the changing the current phase relation by this actually. So so you see, I mean, usually the current phase relation will be symmetrical. Okay, your current and phase will be symmetrical. You have to sort of somehow create some sort of I mean, you have to distort it somehow in order to get a sort of unequal positive and negative response. So that was the bottom line. So then Stuart working groups also, they used niobium with PT, but then they magnetized the PT using a yttrium ion garnet sort of film, so that they did not require a magnetic field. They they magnetized this using a magnetic field. After that, they got this diode effect. Okay. So bottom line is that you need to distort the for a junction to get a non-reciprocal response, you need to distort the current phase relation somehow. Okay. So then this is where our my today's talk, this is where our work is relevant. What is our approach towards a junction, towards getting a sort of non-reciprocal Josephson effect? Most people use actually this RASPA interface. So in planar geometry, for example, here, sorry. Okay, so this slide I skipped, but these are just to show so there are some reviews have come, so people can get more information about those effects. Okay, so this is all right. So RASPA effect is more popular, but what we thought probably RASPA, why is it actually essential? So we took a vertical geometry in which you see this Raspa effect is negligible. So because this Raspa term becomes 0. Okay, so in this vertical, your current is injected vertically. So in the previous junctions that I showed, so that 2022 Christoph Strunk and Stuart Parkin groups junctions, they are planar. Okay, so you have a Raspa field which is perpendicular to the current direction. Okay, so your Raspa effect is maximized. So here it is just the cross product is 0. So there is no Raspa. So, but then this PT has some internal, of course, this is a heavy metal, so it has internal spin orbit coupling. So, and if you send a current through a spin orbit material, you expect so what is called a spin Hall effect. It is very well established now that you send a charge current through a heavy metal, then you expect a sort of spin Hall effect, spin separation. But now here things are different. Here we are not spending just uh, like single particles there. We are not setting normal current. We are now sending super current. Okay. Now super current means you have to couple up and down. So this although this pairing up and down pairing is in the momentum space, but there is a length scale associated with it. The coherence length is a limiting length scale. So you cannot really expect this large spatial separation between up and down spins for singlet. Okay, for if it is singlet. So uh, so there is a problem. So what to expect in this case? So what I mean people have calculated is that and experimental people have shown I forgot to put that reference actually. If you put a superconductor next to a platinum layer or a heavy metal layer, actually you generate a little bit of spin triplet correlation. Okay, so niobium PT, people have done mu-SR measurements actually to show that at the interface of if you just put niobium below transition temperature of the niobium, you generate something called spin triplets pairs inside the platinum layer. Okay, up to certain length. So, so that is the triplet has this up and down components. Okay, so which are polarized. So this is not possible to polarize, but these are already polarized. So there is no restriction on these to be spatially separated. Okay, so these theory papers have argued that way that I mean if you have a supercurrent across this, then you can expect uh, separation of triplets to both sides equivalent to what you have in the normal spin Hall effect. Only difference is that your here it is just the up and down pairs. Okay, so we so that is something called a I mean that so that is something we is called actually supercurrent spin Hall effect. And if you have such a separation of up and down sort of pairs, then you can actually expect some it's a polarized, so you can expect some spin moment. Okay, what it means is that this spin moment will add. So as I said, this current through this junction depends on this relation, this Josephson relation, which is phase dependent. So this moment can generate some additional phase. So if you send current this way or this way, so then you can expect different directions. You can expect a flipping in the direction, and you can expect a plus or minus so the effective current will be added or I mean effective phase will be added or subtracted. So then you can expect a plus current and minus current different. Okay, so this can happen either if you change this current direction, or keeping the current direction fixed if you change the magnetic field. Okay, so in present, so plus field for a fixed bias current, plus field and minus field can also give you a asymmetry between the uh, response. Okay, so that way it is a field, one can generate a field tunable diode effect one can get. But notice that it is dependent on this on this addition or subtraction. So that means if there is no field, so then you don't expect anything. So you don't expect any diode effect in these junctions if you do not have a field. So it's zero field, it is not a diode. Okay, So that was our sort of approach. Okay, so device fabrications. So these are like a bit of a lot of. We start with this multi-layer. Multi-layer means three-layer: niobium, platinum, niobium, and we do focused and combine like optical lithography and focused ion beam lithography to make these devices. So this is the active area of the device, basically this part. Okay, and these are roughly 200, 300 nanometer if you look at the scale. So the scale is about 300 nanometers. Okay, so this is a bit of tedious work, but people have students actually have managed to do this. And the typical response, current voltage response, is like this. And at zero field, so it is perfectly symmetric. So no diode effect at zero field. And if you measure the transition temperature, you see multiple sort of steps corresponding to the transition temperature of different parts of the junction. So the major transition is actually, junction transition is actually this one, which is corresponding to the initiation of Josephson coupling across the platinum layer. Okay, so that is characteristic, like typical sort of Arctic or resonance temperature curve and IV curve. Okay, now so yeah, so then when we did I mean, what we did is that we measured it in different magnetic field. So so this is the critical current measured as a function of magnetic field for a particular thickness of platinum, which is the barrier. So we see that if we subtract plus critical current to minus critical current, so there is a finite. So this red one is actually the difference, critical current in difference. So there is a bit of a diode effect. So there is a bit of asymmetry we already see from the measurement of critical current. And if you from the directly from the IV also you can see here. So this is current voltage curve. This is plus side critical current and minus side critical current. So so we automatically see that okay, this is in a this is not zero field, this is in a finite field. Okay, and so this principle that we are working on is I mean, it says that the thought process is correct, but then our thought process relies on the fact that we have generated some sort of moment in the PT layer that otherwise it would have failed. So we are saying that our interpretation is that there is some moment generated in this PT because of the current we have sent through this because of the bias current. So it relies on this fact that there is a moment on this. Now, so the now the important thing is that, so this observation is like normal, so it's a very easy thing we are seeing, but then it all is true, it all hinges on the fact that there is a moment in PT. Okay, PT barrier. So so we have to prove that there is a moment in the PT barrier. So what it uh, so the I mean, how do we prove that? So that is, yeah, so how do we prove that? So we took two different approaches to prove that okay, there is actually a moment. And one of them is that, see, imagine, so if there is a moment here and the Cooper pair is coming through this. Cooper pair means I'm talking about niobium is singlet, so singlet Cooper pair up down. So then if it is coming through there, then it will feel the moment here, and it will be like it will not know whether it is a ferromagnet or not a ferromagnet, but it will feel a moment. So it will behave, it will feel like I'm going through a ferromagnet. So the response will be like usual ferromagnetic junctions, although this is not a ferromagnet. Okay, so that let me, so what happens in this case it has to be visible here. So the typical thing that we people see in this case is that something called zero pi transition. So this Cooper pair gains some phase while coming through the this, and that as if you do a measurement in terms of thickness, people have seen in SFS junctions also, if you vary the thickness of the ferromagnetic layer, you go through something called zero pi transitions. Okay, and that is exactly what we did. We made a lot of devices with different thickness of this layer, but this is just a picture, but this here in this case it is just PT. Okay, PT layer, so which is non-magnetic, but we still see the so-called zero pi transition. So 0 pi like transition oscillations, similar to SFS junction. I say it again, we are measuring a normal PT junction, but we are getting a response like a ferromagnetic junction, this one. So that is saying that, okay, there is a moment, there is an effective moment in the PT layer. Okay, that is our sort of proof. So it can also be proven in another way, that if you make some sort of a spin valve like device. For example, if we put a nickel, and if we have a moment, nickel has a moment, and if PT is actually generating a moment due to the proximity of the niobium in the superconducting state, so then these two moments have to it can be switched like a normal spin valve, and we see that signature. So if you change the current direction and you do the normal sort of MR measurement, you see that that spin valve like response in parallel and anti-parallel configurations. So I'm not going into the details, but we see that spin valve. So there are like two independent measurements which shows um, that there is actually a moment generated in the PT layer. Okay. So yeah, so that was the data. So what I will conclude with this thing, that this data is actually the first experimental evidence of supercurrent spin-Hall effect. So that this is a magnetic field controlled Josephson diode without using the Rasuo effect, which is the most popular sort of approach to this. And we are seeing 0 pi like transition in purely non-magnetic junction. Okay, so these are this is significant in that way also, but there is a lot more to be understood in this work, of course. Okay, so we have archived this work recently. You can have a look at it. And I have to acknowledge the funding and, of course, the hard work of Devasri to who did the actually work. Okay, have a look at this archive paper for more details, or I am available to. Okay, thank you. Thanks.
So thank you very much for this interesting talk. Actually, I'm not from this field, so please accept my ignorance. So main idea of these things is that basically you want to have a kind of singlet state, which is the superconducting Cooper pair. Now you are actually pushing this from niobium to any kind of non-magnetic layer, and then basically you make some kind of polarization, right?
Yes.
Yeah, and then basically you got a magnetic moment there, which
Yeah.
is actually your spin duplex state, what you are saying.
Yeah.
So the question is that what is the ordered values of this kind of moment of the internal field? Do you have any idea, estimation?
Okay, so that is something that we quantitative estimation is not straightforward, because we do not know, because see, we have just niobium superconducting electrode, then you are pushing some current into it. So we have putting some I current. So there is no way to know what fraction is actually converting into it. So, but yeah, so theoretically also there is no sort of there is no way to. Only thing we can see is that if that fraction increases, your moment should increase, so the response, that thickness dependent response or other responses should scale with that. That's the only. But I don't think that is straightforward to sort of estimate. There is no protocol for that.
Yeah, that is, I can understand. This is
Yeah.
very difficult.
Yeah.
Can
No.
I ask
Yes,
one
please,
more?
please.
Yeah, so then actually the follow-up things that comes up, that means now you have a, as I see that your layers are around 30 or 30, 25 nanometer range?
It varies from 5 to
5
30.
to 35 nanometer range. So now I think there would be a way actually to really see this spin polarization effect. If you, as you already mentioned, probably you already have started to do neon, right?
Not me, that is some other groups have
Somebody else, yeah.
done it. That is, but then it has to be done at the low temperature, when below the transition temperature.
Right, right.
So
Yeah,
that
4.8 Kelvin, you and I will
yeah,
superconducting.
so
Yeah,
so it is possible probably, so that polarization to see, because people who have done this not in this kind of junction, but the MUSR measurement that has happened at niobium platinum interface, they have actually seen this only, but they have not seen a sort of like a moment generated in that. They see triplet correlation, the signature of triplet correlation. So this is very local, but whether that triplet is leading to a moment actually because of separation, that they have not seen.
that would be fascinating.
That would
Right?
be nice.
Okay, thank you
Yes.
very much. So we have a singlet Cooper pair, and now it is when passing through this high spin orbit coupling material platinum.
Yeah.
and it's stated as becoming printed plate. So why the Cooper were not breaking with its making this printed?
No, no. So it's not like so it will be it will be a mix. So it's there is nothing like when the Cooper pair enters this spin. So this theory paper that I have cited. Uh, uh, yeah, this one. So these theory papers I have cited, you can have a look at those. I didn't understand most of it actually, but what the interpretation is that uh, you push Cooper pairs, but then they generate a mix. So because as I said, there is no way to say okay 10% or 50% of pairs will break. So it will always be in a mixed phase. So some of them will probabilistically convert into triplet, and some of them the rest of them will keep moving on. Okay, in a ferromagnet also that happens. Like over length it keeps gaining phase, that's all. So there is no reason why it should immediately break. Even in ferromagnet it immediately doesn't break. So this is not a ferromagnet, this PT is not a ferromagnet, it will not, there is no reason for it to break directly.
So can we see a diet effect in simple NBPT bilayer, or have you done some kind of work in this direction?
No diode effect in NBPT bilayer. So yeah, I mean we have seen some sort of change in TC, but we are not. There is no conclusive experiment that in just in bilayer you have. If you have a magnetic, if you have NB and some magnetic layer, we have seen. So published also people. You can have diode effect, but in a track, you are talking about a track, not a junction. So, but only platinum there is
With non-magnetic, like
no. So actually, without anything, also this Mudera group, if you see, without anything, also because of geometrical effect. So those kind of things are there.
but have you like
No, I have not noticed. Okay, thank you, thank you.